Start. Okay, welcome to this lecture on microscale transport process. What we were discussing in the last class is slip flow. We started working on what we call slip flow. Okay. What we said at the very outset, that depending on what is the value of Knudsen number is lambda by L. Depending on what is the value of Knudsen number, you can be in different regimes. If Knudsen number is less than 10 to the power minus 2, then it would be continuum flow with no slip, and if it is between 10 to the power minus 2 and 10 to the power minus 1, then it would be continuum flow with slip, and then if it is between 10 to the power minus 1 and 10, then it is considered as transition flow between continuum and free molecular flow, and the equation that is used is Barnett equation, and Knudsen number greater than 10, this is referred as free molecular flow, where molecular dynamics, collision between molecules, that will govern the properties. Continuum assumption cannot be taken. Now, what we are doing in the last class is we were trying to solve something which is referred as microquette flow. That means, there is one plate which is moving at constant velocity u, and there is another plate which is fixed. Okay. This plate is moving at a velocity u, and in the last class what we did is, from Navier-Stokes equation, we showed that the solution would be something like this: u is equal to C1 y plus C2, that we have already derived in the last class. That this is a standard form because of certain assumptions. We had taken several assumptions. We had taken translation invariance of the setup, okay, along if this is x, this is y, and perpendicular to the paper is z, then there are translation invariance of the setup along x and z direction. Only u will vary only in y direction, and there is only pressure, there is no pressure present. So, only pressure present is hydrostatic pressure, that is cancelled out with the gravity and things like that. So, with certain assumptions we ended up with this expression u is equal to C1 y plus C2, and what we said is that for no slip boundary condition at y is equal to 0, u is equal to 0, and at y is equal to some value, what did we call last time, h, yes, this is at y is equal to h, u is equal to capital U. So, this is what we have, and with this boundary condition we said that from the first boundary condition immediately we have C2 is equal to 0, okay, and from the second boundary condition we get a value of C1. So, that is how we ended up with this formula u by capital U is equal to y divided by h. Okay. In dimensionless form you can write u bar is equal to y bar. All right. So, this is the formulation using Navier-Stokes equation with no slip boundary condition. No slip means u is equal to, at the wall, the velocity of the wall, the fluid attains the velocity of the wall. That is the idea. Now, if you impose a slip boundary condition, first I mean I mentioned in the last class that this equation remains same. This is the governing equation and this remains same. However, the boundary conditions will not be same. You cannot assume the wall velocity to be same as, or the fluid near the wall will attain the velocity of the wall. This would be somewhat different. So, these boundary conditions will be different. So, the magnitude of C1 and C2 they will be different. So, that is the idea. Now, what we need to understand here is that the gas surface, I mean I need to focus further on gas surface interaction near the wall. I mean, we mentioned there is fluid to be gas here, because gas will have mean free path which is a little higher, and so it is likely that you will be working in this. I mean, this is the regime that we are referring to, and you can for a liquid anyway the mean free path would be less. So, the applicability of slip boundary condition will be more important. The slip boundary condition will be more important for gas surface or flow of gas through a microchannel. So, you have gas surface interaction near the wall. So, what we have here is the sub layer at the interface few mean free path thick, okay. This sublayer is referred as Knudsen layer. This sublayer is referred as Knudsen layer. When Knudsen number is small, when Knudsen number is less than 0.1, means less than 10 to the power minus 1. So, Knudsen number is less than 0.1, the or I should say when the Knudsen number is less than 10 to the power minus 2. So, it should be 0.01. When Knudsen number is less than 0.01, the effect of Knudsen layer is insignificant. So, what does this mean is average velocity and temperature of gas near the wall is continuous and equal to the velocity and the temperature of the wall. Okay. So, if this is the condition, if average velocity and temperature of gas near the wall can be considered, if that is continuous and equal to the velocity and temperature of wall, if this is the case, then you can assume or then you can extrapolate the bulk flow to the surface. However, when you have this Knudsen number which is higher at high Knudsen number, the collision frequency is low. The collision frequency, collision means collision between molecules, that frequency is low. So, what this means is equilibrium between the velocity or temperature of the wall equilibrium between this quantity, the velocity and temperature of the wall, and the same near the wall. Near the wall, this is the other quantity, cannot be established. Cannot be established. So, equilibrium between the velocity or temperature of the wall and the same near the wall cannot be established. Okay. So, in that case, I mean this is possible only when the collision frequency is low. Collision frequency is low when the mean free path is much higher. So, mean free path higher, that means the number of collisions is low. So, unless molecules they collide, if they collide several times, then it would be easy for the equilibrium to be established, but that is not possible if you have high Knudsen number, or in other words you have low collision frequency. So, there would be some amount of discreteness in this process. Okay. So, in that case you have to consider interaction between the gas and the solid molecules, from microscopic sense, not macroscopic. I mean not using continuum, rather you have to consider the collision, the interaction between gas and solid molecules from microscopic sense, because equilibrium has not reached. So, you cannot consider the velocity or temperature of the wall as same for the fluid that is next to the wall. Now, what is done here is we have to introduce two concepts at this point. One is what we call sleeve velocity. The tangential velocity, one mean free path away from the wall, that is equal to, this is considered as u wall plus lambda du dy at wall. What are we doing exactly? Can you guess what is happening here? You are assuming that the velocity next to the wall, the velocity that is attained by the fluid next to the wall, that in case of a no slip boundary condition, we assume that that is same as equal to u wall. Okay. Now, we are saying that it is not exactly u wall, but little different from the u wall. And what is the little difference? So, we said that we are not exactly on the wall, but one mean free path away from the wall. What is the dimension of one mean free path? If you and I can quickly refer for you, lambda of nitrogen at 1 bar pressure, that is equal to 70 nanometer. All right. So, that is one mean free path. Now, if you consider not exactly the wall, but one mean free path distance, that means 70 nanometer away from the wall, and that point you want to know what is the velocity, and what you do is you are assuming, so u wall plus this is the distance away from the wall, du dy at wall. Ideally, if you expand it, there should have been other terms as well, right. So, you are only taking the first order term and not other terms. I mean, you are permitted, right. I mean, if you do not know what is lambda, if I instead of lambda I say h, can you tell me what is the velocity of the fluid? if the velocity at the wall is u wall, what is the velocity of the fluid at distance h from the wall, and if h is small, you can expand it by Taylor series. Now, exactly that is what we have done. Only thing is, we have only picked up the first order term and not the higher order terms, and that is what is referred as first order slip condition. First order, this is referred as this condition, this is referred as first order slip flow condition. First order slip flow condition, all right. And this is now, this is what we are going to call the slip velocity. This is what we are going to call the slip velocity. It is not exactly the same. I mean, now we will tinker, now we will play with this equation further, but essentially first order, and why first order you understood, why we are calling it a first order, but this is not a final form of slip velocity. Now we will play with this. Let me define couple of quantities here. One thing we must appreciate, that if this is the wall and if this is the molecule, this comes and hits here and then it gets reflected. That is the idea, right? We are talking about molecule, collision of molecule, gas molecule with the solid wall. So, this is what we are referring. So, what we can write here is that the incident molecules carry tangential momentum. And there is one term called tangential momentum accommodation. It is quite a long term, accommodation coefficient. I have not, I know so many coefficients, this is really the long, so many words in the one coefficient. Now, this is tangential momentum accommodation coefficient. This is given as sigma v, that is equal to tau I minus tau r divided by tau I minus tau w. What are these taus? Tau I is equal to tangential momentum of incoming molecules, tau r is equal to tangential momentum of reflected molecules, and tau w is equal to tangential momentum of wall. Okay, so, if you have these tangential momentums, if these are defined, but the point here is that these molecules carries with it some amount of tangential momentum, that means momentum in this direction, and then you have the wall itself may be moving or wall itself can be static. So, if the wall itself has a tangential momentum and incoming and the reflected molecule. So, this is the accommodating these terms, one has some coefficient known as tangential momentum accommodation coefficient, which is defined by sigma v. Now, what we have in this case is, instead of writing these as the slip flow velocity, these as the slip flow velocity, okay, instead of writing these as slip velocity, what we write in I mean, which is more I would say more comprehensive, more detailed one, is the expression for slip velocity for an isothermal wall, of temperature Tw, there is a slip velocity given by Maxwell, slip velocity expression given by Maxwell. This gives u gas, which is the slip velocity, minus u w, which is the velocity of the wall. I mean, if you think that wall is fixed, then you will consider u w to be 0, no problem, 2 minus sigma v divided by sigma v lambda del u del y. What do we have? This came as a first order slip flow condition using Taylor series expansion. Then they said that okay, I need to add some accommodation coefficient on this expression, and that factor being 2 minus sigma v by sigma v. Okay. These they have shown, I mean, by some other consideration, that is why we already mentioned name of a scientist here. Now, more importantly, for monoatomic gases, u gas minus u w, this quantity u gas minus u w, that would be equal to that factor 2 minus sigma v by sigma v remains same. However, the lambda, the mean free path, that has an expression for monoatomic gases, and that expression is mu square root of pi divided by rho square root of 2 r T w. This is an expression for mean free path. This is an expression for lambda for monoatomic gases. You need to check the book on physical chemistry to find out how they arrived at this for monoatomic gases, the expression for mean free path. Anyway, that is not exactly under the this you can figure out. This is how this expression for mean free path is obtained. Check the book on physical chemistry. Now, so this is the expression for monoatomic gases, that u gas minus u w is, there is a factor which has been put there because of this tangential momentum that incident molecules they bring, and then this del u del y, this is arising from Taylor series expansion, and this is the expression for lambda. All right. So, if somebody wants to know what is the slip velocity, then this is the slip, this u gas is the slip velocity, and u w, if it is a fixed wall, then it is 0, and for the wall that is moving at a constant velocity u, then u w will be capital U. So, this is the expression for first order slip boundary condition given by Maxwell. Now, if we have this information at our, if we have this information with us, how do we solve this problem? What was the problem? U is equal to C1y plus C2. We said that remains same, right? Navier-Stokes equation for what? We said it is basically one plate is fixed and the other plate is moving at a velocity u, capital U. In that case, the small u, the velocity at any location y starts from, y goes vertically, y is equal to 0 at the fixed plate, and it goes up, and y is equal to h at the moving plate. So, this is the boundary condition, and this is the this is the governing equation, and the governing equation remains same whether you have slip or no slip. That is what we said. Now, if we have this as the boundary condition, how will you put this boundary condition inside and come up with the values of C1 and C2? That is exactly what you got, right? Last time what you did the same thing, and you have gotten C2 equal to 0 and C1 is equal to some value 1 by h or u by what did you get? Y is equal to h means u is equal to capital U. So, it is u by h. C1 is equal to u by capital U divided by h, and y C2 is equal to 0 for no slip boundary condition. So, now you have to put these expression to this and come up with the generalized expression for velocity in case of that micro Couette flow. So, how do you do it? We write here, let us say we write u is equal to u by u w. We try to make this dimensionless, and y is equal to y by delta. I mean, delta is equivalent to h. I mean, just because that we have moved from no slip to slip, just because we have considered instead of a macro channel, a macro case to a micro case. So, instead of h, we are writing this as delta. So, we have these, our basic structure remains same, that means we have two plates. So, one plate is moving at a velocity capital U, and this distance is delta. Okay. So, let us write u as u by uw. I mean, don't I mean we should have given some other name, but we are not doing it. I thought we are mature enough to play with this. So, y is equal to y by delta. Now, in that case, and the Knudsen number would be equal to lambda by delta. Okay. So, if we start from this expression, okay, this is for monatomic gas, we do not need to, I mean we let us write the general one. Now, what we said is that u at the or we call this u s, say u s minus u w, okay, u at the surface minus u w, which is the velocity of the wall, that is equal to 2 minus sigma v by sigma v into, let me write this as Knudsen number del u s del n. What is n? N is basically normal to this plate. Okay. So, n is equal to y here for this problem, n is equal to minus y for this part of the wall. Okay. N is the normal. Okay. So, we can write this further, we can and why are we getting into Knudsen number, you understand that, right. Knudsen number is lambda by delta, and then we have already y is equal to y by delta, and n is equivalent to y when it comes to this direction, n is same as y, and when it comes to this plate, n is equal to minus y, because n normal is against the direction of y. So, this you understand that then why we have Knudsen number, because this delta will cancel with this delta. All right. So, instead of writing it as lambda del u del y by delta, we put the delta inside and make it Knudsen number. Now, if we or we can write this as alpha del u s del n. Let me write this further. I mean, if I split this into lower wall and upper wall, what do we get? Lower wall, you have u w is equal to 0. U w is equal to 0. Okay. So, what that and u w is equal to 0, and not only that, you have del u s del n is equal to del u s del y, because y and the normal, they are in the same direction. All right. On the other hand, at the upper wall, you have u w is equal to 1, because what is the definition of u? U is equal to u divided by u w. Okay. So, u w is equal to 1, and in that case you have del u s del n, that is equal, and other than that you have other than u w is equal to 1, you have del u s del n is equal to minus del u s del y. All right. So, these are the conditions, one is applicable at the lower wall and the other one is at the upper wall. Okay. Now, if you write that at y is equal to 0, if you write that at y is equal to 0, at y equal to 0, you are saying that u is equal to, at y is equal to 0, u should be equal to, you had C 1 y plus C 2, that is equal to nothing but C 2, right, y goes to 0. So, this is nothing but C 2, and what is now the u as per the slip boundary condition? As per slip boundary condition, these u would be what? This u would be, we need to look into this expression. This u would be, u w will go to that side. So, it would be u w plus alpha del u s del n, u w is equal to 0, the wall velocity condition is 0. So, what do you end up with? What do you end up with? You end up with this u is equal to 0 plus alpha del u s del n at wall. Right. One is this, we are assuming uw to be 0 at the lower wall at y is equal to 0, and on top of that we say that at lower wall del u s del n is equal to del u s del y. So, using this we are writing this as 0 plus alpha del u s del n, that is equal to alpha del u s del y at y is equal to 0, right. And what is this del u s del y? If we take a if we know that u is equal to c 1 y plus c 2, and if you take del u del y, that is equal to c 1. So, what do we have? Alpha into c 1, all right. So, alpha into c 1. So, we have one expression, that is c 2 is equal to alpha c 1, that is one expression we have in at our disposal. What is the other one? Other one is that at y is equal to 1, you have u s, that is equal to u w plus alpha del u s del n. Same thing we are doing. What we have done last time, we are using that same expression, u w goes to the right hand side. Okay. Now, only difference is that here u w is equal to 1 at the upper plate at y is equal to h, number 1, and number 2, this del u s del n and del u s del y, there is a change in sign. So, these are the two things we need to remember. So, here you will end up with this is equal to 1 minus alpha c 1, right, 1 minus alpha c 1, and what is u s? Here in this case u was c 1 y plus c 2 is equal to c 2. Here in this case it would be what? C 1 plus C 2, because C 1 y, and in this place at this place y was 0 at the lower wall, at the upper wall y is equal to 1, y 1, because we have defined y as y by delta at the very beginning. So, you have C 1 plus C 2. So, you have two expression, one is C 2 is equal to alpha C 1, and the other expression is, if I take this back again, I write here C 1 plus C 2 is equal to 1 minus alpha C 1. This is the other expression, all right. Now, you solve these two expressions, C 2 is equal to alpha C 1 and C 1 plus C 2 is, I mean solving does not, it is no big deal, because you can put this C 2, instead of C 2 you write simply alpha C 1, instead of C 2 you write alpha C 1. So, everything in terms, so you basically eliminate C 2, and so what you end up with in that case is I can write here as C 1 into 1 plus 2 alpha, that is equal to 1. All right. C 1, you bring all the C 1s to the left hand side, and so you get C 1 into 1 plus 2 alpha is equal to 1, or you get C 1 is equal to 1 by 1 plus 2 alpha, and C 2 we had alpha C 1, that means equal to alpha by 1 plus 2 alpha. So, earlier we had what? We had C 2 is equal to 0 and C 1 is equal to we had capital U divided by H, but now we have some other quantities. So, if somebody now wants to write what is the expression for U, he will be writing U is equal to 1 by 1 plus 2 alpha into Y. U is what? C 1 y plus C 2, right? That was the expression for U, general expression, but now we are putting this C 1 and C 2. So, U is equal to 1 by 1 plus 2 alpha y plus alpha by 1 plus 2 alpha, that is a C 2, that is a constant. So, this is the expression for U, considering slip flow boundary condition. You can simplify this further, and probably the one because alpha is your creation, alpha is not something which is I mean alpha is basically some variable you clubbed together. So, if you remove them, you get, because originally sigma v is something which researchers who are working in this area they understand. So, this divided by 1 plus 2 into 2 minus sigma v by sigma v into Knudsen number. So, this is probably the expression that is it is basically another form of this expression. So, what was the continuum flow? U is equal to y, corresponding continuum flow expression was u by capital U is equal to y by delta or y by h, and in dimensionless form it is u is equal to y, and in dimensionless form the slip flow condition gives u is equal to this expression, and this expression is meant for then what? Meant for this microquark flow. You have two plates, the upper plate is moving at a constant velocity and the lower plate is fixed. Okay. So, this is how you do it. Now, if somebody wants to know what is the now if you want to draw how this whole thing looks, this is the plate that is moving at a constant velocity u, and this is the plate that is fixed. Okay. So, if you have a slip, if you have no slip boundary condition, you can expect these to be the velocity profile, right. Velocity is 0 here and velocity is capital U here. That is the no slip boundary condition. Here also, since we are retaining this u is equal to C1y plus C2 form, that means the velocity profile in this case will also be linear. Can somebody guess then what would be the form? It will not be 0 here definitely. So, it will start from here and it will end before this. So, it would be like this. So, this is the slip flow solution and this is the no slip. Now, if somebody wants to know what is the volumetric flow rate per unit depth, depth is perpendicular to the paper. If somebody wants to know the volumetric flow rate per unit depth, okay, and if somebody wants to know the non-dimensional, these in non-dimensional form, then what he will do is he will find this q running from 0 to 1 u dy. That is the expression. If somebody wants to know that you have one plate fixed, other plate is moving, now this fluid that is pushed downstream, what is the volumetric flow rate per unit depth perpendicular to the paper? Okay. That commonly we try to find out. And here what we find is if you want to do it in a non-dimensional form, it would be integration of 0 to 1 u dy. Okay. Now, it would be your task when you go back after the class, integrate this between 0 to 1 u dy and see that this value is equal to 0.5 and check the same thing with the continuum solution, and you will find that it is the same value you get for continuum solution as well. Okay. So, that you need to do it yourself. So, the conclusion that we draw is that volume flow rate here is independent of Knudsen number. This is very important thing. I mean, you have from continuum flow, you found out some volumetric flow rate. Okay, you have fixed plate, you have moving plate, and you found some volumetric flow rate. What this says is, even if you did all these things, first order boundary condition, etc., the volume flow rate remains same. So, whatever you had from continuum solution, that was good enough. So, that as far as the volumetric flow rate is concerned. So, this is independent of Knudsen number. This is, I think, something very important you need to remember. Now, this is for a microquark flow. Similarly, you can have something called a micropoisely flow. This is not this should be pronounced properly. This should be pronounced properly. and this I mean we need to check the pronunciation. Now, this micropoisely flow, this if somebody wants to solve the same thing that you have done here for microquark flow, instead of that, if you do it for a flow through a tube, flow through a capillary, and instead of no slip you want to go for slip boundary condition, then what kind of expressions you end up with, that I would like to I mean I would not solve it from the way we have done it here. What I will do is I will just give you the final expressions, and that is all I would like to say here. Now, the Navier-Stokes equation in this case will be settled to this form. Okay, this form, and so the solution here is Reynolds number divided by 2 dp dx, that is the pressure gradient, y square plus C1 y plus C2. This is the form of velocity. I mean, you remember what was the velocity we have been working with, parabolic velocity profile, etc. There we have a similar quantity. We have something into 1 minus r by r whole square. That something we call this as 2 u 0. Sometimes we call this u max. So this is the type of form we have. If we want to write it in a generalized manner, instead of r, if we write it in y, we end up with an expression something like this. Now, here if you do this same exercise with slip flow boundary condition, I mean if you bring in the concepts that we discussed here, you will end up with an expression which looks like this. And the corresponding continuum solution is so this is the continuum solution, and this is the first order slip flow solution. Okay. So, this is the first order slip flow solution and this is the continuum solution. One can make some note here, is that dp dx is always negative, is negative. Okay. So, if dp dx is negative, then one has to have this quantity Re by 2 dp dx into 2 minus sigma v by sigma v into Knudsen number. That means, the additional term that you have because of first order slip flow solution. Now, this is negative, means minus of this quantity, this would be positive. So, what that means is that this quantity, this extra term that you have, minus Re by 2 dp dx into this term, that is positive. That means, first order slip flow condition gives higher flow speed. That is one conclusion you draw here. Okay. Also, in case of a Poiseuille flow, in case of a flow through a capillary, what you need to, I mean, what would be another thing is this U max. In case of micro-couette flow, this was not important, but flow through a capillary, you know that at the center the velocity is maximum and all kinds of things. So, you have a similar exercise you can do with U max. As a matter of fact, you can obtain this U max as equal to minus R e by 2 dp dx into 1 by 4 plus alpha. One can see this alpha is of the same meaning as we had done earlier. In case of a micro-couette flow, we had a definition of alpha. So, one can come up with this expression, one can come up with this U max expression. So, all these exercise that we do for macroscopic flow, these exercise can be done with this first order slip flow boundary condition. So, what we said at the very outset, I would like to go back once again, because after, I mean, today we are going to end this discussion on slip flow and we will move to another topic. What I would like to say at the very, what I had already said at the very outset is that there is this continuum flow with no slip, then there is continuum flow with slip, and then there is transition flow, and then free molecular flow. Now, this free molecular flow is ideally what you should be considering, and continuum flow is at the other end. So, if you look at the entire spectrum, on one end of the spectrum it is the continuum flow, and the other end of the spectrum it is the free molecular flow, which is the collision between molecules and molecular dynamics. However, this is computationally, it requires a lot of effort. I mean, by if you want to track say thousands of molecules, okay, for say hours, I mean computationally just tracking the molecules, tracking the velocities after each and every collision, it is a tremendous task. So, in fact, continuum flow is basically you make some assumption and then the process of arriving to the solution is much simpler, but you make certain assumption in case of continuum flow. So, you are in between these two bounds. Okay. So, when you work with macroscopic fluid mechanics, you are in continuum flow, and when you are in molecular dynamics, you are in free molecular flow. Now, where this slip boundary condition or whatever we discussed today as first order slip, that stayed somewhere. That is basically what we call a make do approach. I mean, you have I mean, you know that you are not doing the right thing, the rigorous thing would be free molecular flow, or if you can make the other rigorous thing would be continuum flow, based on which you are writing this Navier-Stokes equation. Now, these slip boundary condition here, you are kind of, you know that you are in a regime where continuum flow assumption cannot be taken. However, you do not want to invest that much of effort in getting into the free molecular flow. So, you are somewhere, so you come up with a with an approach which is more sort of practical. You come up with an approach which is where you do not require that much of computational time, and at the same time you do not leave out all the understanding of continuum flow. So, this is definitely, this is not 100% rigorous. However, this gives you the right I mean, by balancing these you can learn a lot of these you can get a lot of insight into this kind of flow. So, today I would like to stop here. Basically today I would like to, from the next class, what I would be doing is I will be talking about something called a microstructured reactor. There what I will essentially tell you how we can simplify various fluid flow and heat balance equations, because in a I remember when I introduced this microstructured reactor, I mentioned about this a honeycomb type structure. You might have already you can recall. it is like a honeycomb structure. Instead of a randomly packed bed, what we will have here is very specifically machined channels, okay, and these channels will be acting as a reactor. And as you so as the fluid flows through these reactors, they will have they will have the fluid flow issues, they will have the heat transfer issues, and they will have this reaction going on simultaneously. So, how to I mean, of course, you can very well say we can start from first principle, pick up the best model that we have in from CFD and solve this, but we should what we have to do is we need some approximate method, some method to quickly come up with some solution, so that we can compare various geometries. I mean, we should not we are talking about thousands of such channels running parallelly. So, there are some I mean, people have established some method to use best of everything. I mean, basically it is partly a CFD model, but not as rigorous as a CFD model should be. Some amount of approximation they put in there, and they come up with a solution, and then they try to find out if you would have gone for a rigorous CFD model, how much we differ from the actual solution. So, that exercise I will get into in the next class. I think I will require just one class for that, and beyond that point I will be talking about immiscible flow through microfluidic channels, flow of bubbles, droplets. We have two phases which are immiscible, and if you have that kind of flow through a microchannel, what is the result? So, that is something which I will be taking up next. So, next class, that means tomorrow's class, we will be talking about this microstructured reactor, and I will identify quickly what all assumptions you can make from the most rigorous CFD model to get a quick solution. And from next to next class, we will be getting into this immiscible flow through microchannel, and that is going to be the last topic very likely. That is all I have for today. Thank you very much.